Ma'am, you are not properly audible. Your voice is not clear. Yeah, ma'am, audible. Ma'am, audible.
it cannot be the average of its neighboring points and also be a maximum. Okay? So this is already telling you that Laplace equation does not allow any maxima or minima. That means in a region where there are no charges, and if you have the potential, if you have some surface enclosing a region where there is no charge, so in the central region, the Laplace equation holds, right? And there can be no maxima or minima of the electric potential. Whatever maxima or minima, if it exists, it should exist on the surface, okay, on the extreme points. So if you have a sphere, there should not be any maxima or minima inside. The maxima or minima should lie on the surface of the sphere. So, like if you consider this case. So this is already telling you that Laplace equation tolerates no maxima and minima, and we'll see that this is very important when we talk about uniqueness theorems. It is this property which finally leads to the uniqueness theorem, which again allows us to use the image charges. Okay, so all these things are connected. Now let us see how to solve Laplace equation. Okay. So if you have basically Laplace equation is, so we will try to solve questions where you know the potentials at the boundaries, but we don't know the charge. So there is no charge inside. Okay, so you have some boundary covering or enclosing a region, and there is no charge inside the region. You want to find what the potential is inside or outside. Okay, but the boundary conditions are given, so that's what is known to us. If the boundary conditions are given, how do we use Laplace equation to find potential? So that's the two problem. So here, see, you have two infinite planes, okay? Two infinite rounded metal planes, and they lie in the x z plane, as you can see, at two different z values. One is at equal to 0 at x y equal to 0, another is at y equal to 8. Now you are asked to find the potential inside this slot. Here you can see that there is an infinite strip which is maintained at a specific potential V0, okay, this black region. So that means if we write the boundary condition, this is how it looks like. So at e equal to 0, b is 0 when y is 0. Okay, so this plane. Again, b is 0 when y is a. It's the top plane. Then b is equal to b naught y when x is 0, which talks about this infinite strip. Okay. And b tends to 0 as x tends to 0. These are our boundary conditions. Now, based on this boundary condition, we want to solve the Laplace equation, which will give us the potential somewhere inside the slot. Okay. Now, because you can see that your potential is now a function of x and y, we first try to write the potential in terms of a product of two independent functions. Okay. So, v is equal to x into y, where x is primarily a function of x, y, capital Y, is a function of y. Okay. So, now if we use this form of potential and place it in the Laplace equation, you would get something like this. Okay. Now, in order to solve it, what we will try to do is we'll try to, so what we want is a separation of variables. What we mean by that? So individually, this term we want to make like for this term we want it to be a sole function of x. While this function, this term, the second term, we want it to be a sole function of y. So what do? We divide both the terms by the potential, which is equal to xy. Right? And this is what we get. So now the first term is a function of x only, and the second term is a function of y only. So that means you can write it in this form. Now, because you have written it in this form where this is just a function of x, this is just a function of y, this is telling us that for this to hold, your fx and gy should be a constant. Right? Because suppose if it was not a constant, that means if you just keep y constant and keep varying x, what will happen? Your fx will change. Now, if your fx changes while your gy remains the same because you have not changed y, that means this would no longer be 0. Right? So, for this condition to be always true, your fx and gy should be individually some constant values, and the constants should satisfy this condition. So, if this value is equal to c1 and if 1 by y is square is equal to c, 2, that C1 plus C2 should be equal to 0. Okay. Now, what do? Is we take this constant to be something like k square. Why do we take it as k square? It's because it makes the, makes it mathematically simplest. Okay, we'll see why. So now what we consider is the square x square x and x square y k square is equal to minus k square. Which one? So out of x and y, any one of them can be considered to be k square and one of them to be minus k square. Right? But how do we choose it? Depends on the boundary condition. So why? Because see here, if you solve it, so for the positive constant, you would get an expression like this, right? And for the negative constant, you would get an expression like this. Now, if it was other way around, you would see that the first two conditions will never be satisfied, right? So just look at these two boundary conditions, which says that the potential should go to 0 at y equal to 0 as well as at y equal to a, which means if it is an exponential combination of exponential functions, this cannot happen, right? So that means the y term should have a minus k square constant, right? So that's how we choose the constant, one to be positive and another to be negative. And now this is the general form that we get. So this is dxy is the general form of potential that we get for such a two-dimensional problem. Now, based on our boundary conditions, we try to simplify this term. So what we do first is that, see, here it says that as v tends to 0, as x tends to infinity, your v should tend to 0. So this is already telling us that if your a is a non-zero quantity, your potential cannot go to 0 as x tends to infinity. This term will exponentially rise. That means a should be 0 in order to satisfy the fourth condition. So that simplifies our expression for the potential to this expression. Right? So now what we do, we apply the next condition. What is the next condition? It says that again v is equal to 0 when y is equal to 0. Right? So if potential has to be 0 when y is equal to 0, your this term, the potential, the exponent, the coefficient t should go to 0 because cos 0 is 1. So otherwise this term will always remain, right? So that means for condition 1 to hold, your t should go to 0. So what you are left with is this. Now you apply this boundary condition which says that your potential should be 0 at y equal to 0 as well as at y equal to a. Right? So that means for any values of sine ka going to 0 will satisfy that condition. So that gives you the possible values of k, which is equal to n pi by a, where n can be any integers. Right? So now that means for whatever values of n, you can always write this. So you can have different, right? So you can have sine n pi by a, like putting k is equal to n pi by like n equal to 1 or n equal to 2. So accordingly, you can get multiple solutions. Now, all of them individually will satisfy the Laplace equation. So that means a linear combination of these solutions will also satisfy the Laplace equation. So the general form will then be a linear combination of all such solutions. Okay. Now, if you remember, we talked about the first condition, we talked about the second condition, and the fourth condition. We are yet to satisfy the third condition. So what we do now, we say that now this is our general form at x equal to 0. Your this expression should go to v naught. Right? That is the third condition. So at this point, we use a trick, which is called the Fourier trick, which comes from the fact that our sinusoidal functions that's here, these functions are orthogonal. Okay, so we use the orthogonality of the sinusoidal functions in order to find this coefficients Cn. Okay? And this is the orthogonality relation. So we multiply both sides by sin n prime by a. Okay, and use the orthogonality relation. So that simplifies the left hand side, and you finally get this expression for exponent, your coefficients, right? So now if you put the values, you see that these exponents will be zero. For this particular question, it goes to zero for n, for all even values of n, and goes for odd number. So when n is odd number, you get a non-zero quantity. Okay? So what you do next is you replace that value in your general expression. Okay? This is your general expression, so you replace it here. So this is finally the potential that you wanted to find. Now, based on what systems? In this question, it was a sinusoidal function, and we used the orthogonal relations of sinusoidal functions. We would see that when we talk about spherical polynomials, we have Legendre polynomials, and there we use the orthogonal relations of Legendre polynomials. So based on our system, this system of solving the Laplace equation will always hold. At least it will always hold, given the condition that the set of functions that you choose, so this set of functions that you have, like for this case it's the sinusoid, they should be complete, they should form a complete set, and they should have an orthogonality relation. As long as that holds, you can use this method. Okay. So now, similarly, we can try to solve other questions, like for, okay, before that, let us do a continuation of our expression where we say that determine the charge density on the strip at x equal to 0, assuming it to be a conductor at constant potential. So till now we have found the potential, how the potential looks somewhere inside the strip. The next question says that what would be the charge density at this strip, right? What would be the charge density at this point and y at x equal to 0? So any idea how to solve this? So we know the potential. How do we find the charge density? Right? So what should be the relation based on our previous understanding of Gauss's law and all that we spoke about conductors in the last class. So based on our current knowledge, if we know the potential in the region, okay, and there is a surface, a conducting surface, and you are asked what is the charge density on the surface. So can anyone of you tell me what the relation, what should be the relation?
Ma'am, can we discuss problem?
Yes.
Ma'am, can we discuss problem number 6 of assignment 4? It is related to the surface charge density.
Okay, so we'll come to those questions, but so this is how we are trying to. I don't know exactly what the question number 6 is.
No, ma'am. Just I want to the fundamentals that we can use to solve this problem.
Please repeat.
Basics of question number 6.
Okay, so what I mean is I have seen the last year questions, and there I saw what kind of questions are there. So what we're trying to do is to build the
Ma'am,
concept.
there is too much. Ma'am, please pardon me. There are too much echo in your voice. Too much echo. Maybe two devices. Too much echo. Maybe two devices are parallelly on.
Okay, 1 second. Because I have switched this audio off for this. Yeah, this audio is off. I don't know if others are also facing the same issue, or is it just you? Can others? Because I don't know how to do this, because everything from my side is just same as the same.
No, voice is coming, but there is too much echo there.
Okay. I really don't know how to solve this issue because it's just the same configuration as other days.
There is some delay in the voice also.
Okay. How bad is it for the other guys, like others who have joined? don't know actually. You can try to rejoin and see if the same problem is not, because everything from mine is just the same. Okay. So
Let's
anyways,
yeah.
what
Please continue. Please continue, ma'am. Please.
yes. So what I meant is that we are trying to build on the concepts, and we try to discuss some of the similar questions so that it might help you understand. Exactly what question number 6 is, I am not sure for your current assignment. Okay, I had checked the last year's assignments. So basically, now this question talks about, I think there are similar questions where you know the potential in a region and you know the charge density. And this is not just for your assignment, this can come in any case. So the point is that if you know the potential in a region and you say that there is at one end or at one boundary you have some conducting surface, you are asked to find the charge density on the conducting surface. Okay? So there should be some relation between sigma and the potential, right? So let me recall and remind you guys, we discussed that if you have a conducting surface, we talked about how the normal and the tangential components of electric fields change when you have a conducting surface, right? And if you have a charge on a conducting surface. So if you remember, the normal components had a discontinuity, okay, which was given as sigma by epsilon naught. So if you have a conducting surface with a charge density sigma, E above minus E below was equal to sigma by epsilon naught for the normal components, while the tangential components were continuous, right? So that means if we know the electric field, we can say that the electric field should be equal to sigma by epsilon naught, right? Now, how is electric field related to potential? We know that electric field is equal to minus grad V. So that leads us, so this is our potential, which we derived from the last question, right? And now, because E is equal to minus grad V, this is the relation that relates the charge density with the potential. So that means if you now have the expression for the potential, what you can do is you can do a derivative with respect to x, because here you're talking about x, okay, the strip likes x equal to 0. So what you do, you'll do a derivative with respect to x and then find the value of the derivative at x equal to 0. Okay, and that will give us the value of basically electric field. Okay, and then there's the epsilon naught, which finally gives us the charge density, right? So that means whenever you have a potential, you can use the potential to find the electric field and then use the relations of boundary conditions for electric field components, where it says that the normal components have a discontinuity of sigma by epsilon naught, find the charge density sigma, right? Is it clear to all of you?
Yeah, ma'am. What is del V upon del N? What is represent here?
So N basically means the, you can say the normal component. So if you have a surface in the xy plane, then it will be
okay
in the z direction. So suppose if you have a surface, a conducting surface in the xy plane, then the normal component, the direction of the along the normal will be given by N, right? So in this question, what it is, if I go back, it is along this surface, right? So that's why your normal component is along x. Consider the black strip. It is in the yz plane, right? So the normal is along x. So that's why you do a derivative with respect to x. Yeah.
Yeah, ma'am. Clear.
Okay. Okay. So now let us do a similar problem. But here, what happens is you have another surface. Okay. So as you can see, you have boundaries on four sides. And now these boundary conditions are such that your it has a symmetry in the x direction as well. So the potential at x equal to b is equal to the potential at x equal to minus b. Okay, and that is equal to v naught. And then you also have b going to 0 at y equal to 0 and y equal to a. These are our boundary conditions. Now, based on this boundary conditions, if we start with what we had initially, so the same Laplace equation because it's in 2 dimensions. So we are working with our boundary conditions are in 2 dimensions. So we will work with 2 dimensional Laplace equation, and these are the boundary conditions. Now, that means the general form will be something like this. Now, based on this conditions that we have, can you tell me how to include these conditions in our general potential expression? So let us start with the fact that there is a symmetry in the x direction. What does it tell us? So how do we include that symmetry in our solution here? So how should this A, B, C, D vary? Because of the fact that x equal to b and x equal to minus b, the potential is the same. Any idea?
No, ma'am.
Okay, so let's try to see. See, what it is telling us is that if we put x equal to b, we would get some expression, and if we put x equal to minus b, we should get the same expression, right? So that is telling us that if we just look at the x function, or the function which depends on x, your a and b should be equal, right? Only then the symmetry will hold. So that means we can consider b to be equal to a, and because it is the same constant, we can consider it, like we can include that constant in our c and d, right? So basically, what happens is your a is equal to b. That means take a common. So what you can write is e to the power ax plus e to the power minus ax can be written as 2 cos I to the ax. Okay, and then we can absorb 2a into c and d. So this is how it looks like. So now we have taken into consideration the symmetry along the x direction. Okay. Now again, if you look at the first condition, b equal to 0 at y equal to 0. So what is this telling us? So because b is equal to 0 at y equal to 0, that means again this term should go to 0, right? Because cos 0 is 1, so b must be 0 for this to hold. So that means we would get something like this, right? Now this condition is yet to be considered, right? So what we do is now similar to the last case, we consider that for all possible values of all possible values for different values of n, all of them are individually solutions of the Laplace equation. So we take a linear combination and then we apply this boundary condition which says that at x equal to b, your b should be equal to b. Right? So this is similar to what we discussed in the first problem. And here again, we'll again use the orthogonality condition, okay, the Fourier trick, in order to find the coefficient, right? And this is how the coefficient turns. So that means if you now find the expression for the coefficient, just replace it here, and this will give you the coefficient for this case, right? Okay. Now, if we get a similar question, but now there are the 3-dimensional problem where you have this boundary conditions given in all this, then you have to go to 3-dimensional Laplace equation. The procedure is the same.
Excuse me,
Let's
ma'am.
write it. Yes.
Excuse me, ma'am. Can you show the
Yes,
final solution for the previous problem you discussed? The final. Yes. Thank you. Thank you, ma'am.
Yeah.
Yeah,
Please
please continue.
Here we are briefly discussing the steps, but it's always to try directly solve each step and see how it comes out, because I think that practice will be good. Okay. So now what happens when you have a 3-dimensional Laplace, 3-dimensional problem? So you have the 3-dimensional Laplace equation. Okay. Again with the boundary conditions. So you know how the boundary conditions is specified in the different directions. Okay. But here, because it's 3-dimensional, we have to be careful about how we choose the constants. right? So again, we consider the separation of variables. We divide by b, so we get three independent functions of x, y, and z, and each of them should be constants, such that c1 plus c2 plus c3 should be equal to c2. So till this, everything is similar to what we did for the two dimension. Okay, but now we have to choose the constants. So how do we choose the constants? Now we consider two variables. Okay, so we consider it to be, so we consider one of the constants to be k square plus l square, and others to be minus k square and minus l square. How do we choose this combination? Depends again on our boundary condition. Right? So if you look at y, we see that b goes to 0 at y equal to 0 as well as at y equal to k. That means it should have some sinusoidal or some cosine dependence, right? So that's why we take this minus k square for the y variable. Again, similarly, for z, you see that b goes to 0 at z equal to 0 as well as z equal to b. So that's why we again have a minus l square constant with z. That means for x, it should be b square plus l square. Okay? So then again, it's similar. So these are in solving individual equations, and this is how the individual solution should look like. So that means the overall form should have a form like this, considering each of these boundary conditions. So these steps are quite similar to what we did in the last case. Basically, if you write these are the entire b will be x into y into z. So that is the most general form of b, and then try to put this boundary conditions. Okay. So in that case, what will you get? You will get something like this. Okay. So here you can see you have two such variables, right? So you have n equal to 1 to infinity, n equal to 1 to infinity, because you have to consider individual sets of sinusoidal functions for y direction as well as for z direction. Okay. And then now you can try to put this condition that at x equal to 0, your v is equal to v0. So if you do that, this is how it looks like. So here again, you will try to use your Fourier trick. So this time you have to use two orthogonality relations, one for y and one for z. Okay? And you can similarly find the coefficients. Once you find the coefficients, then you can write include the expression for the coefficient in the most general form, and that will give you. Okay? So these steps are quite similar, just you have to be careful about how you choose your constants based on the boundary conditions that you have, okay? And try to use the Fourier. Okay, now this is a similar question, but here what it is said is that the potential has a different form. Okay, initially it was some B naught for the entire region. Now it is said that it has some B naught from 0 to a by 2, and then it's minus B. So this changes only the fact that this everything would be same, right? But you only have to now change this part, right? So till this, everything remains the same. For the final part where you actually equate the potential at x equal to 0 to the given boundary condition, there you have to consider these two integrations, right? So that's the only change that you do from the first question that we discussed. So based on what boundary condition you have, try to include that in the expressions. Okay, and I'm not going into the details of the steps, but if you try to solve it out, you'll see that you'll get the coefficients, and the next step is the same. So basically, you understand the process of how to solve such kind of Laplace equation problems for rectangular coordinates, right? Any confusion here? Okay. So now let us move to spherical coordinates, and this is very important because when we talk about spheres, okay, so you have to write the Laplace equation in the spherical coordinates, and this is how it looks like. Okay, and considering you have azimuthal symmetry, which in most simple cases do happen. So what you will do is your this term will go away. So what you have is this. So just like in the last case, we did separation of variables considering functions of x, y, and z. here we'll consider B to be products of functions of R and theta. Okay? And try to similar changes such that we have individual terms which only depend on R and which only depend on theta. Okay? And then again, this individual terms should be some constant, and we take that constant to be L into L plus 1 and minus L into L plus 1. Why this form will again be clear. It has mathematical implications, so it makes solving the problems easy, and that's why we take this form. Okay? Why? Because now if we try to solve this part of just for the radial component, we have a equation like this. Okay, and it has a general solution which looks like this. So this is your function which just depends on the radial group. Similarly, you have a function which depends on the angular part, which is theta. Okay, and this is how it looks. Now, the solutions for this equation is actually Legendre polynomials, which, so if you want to find the the expressions of the Legendre polynomials, you can use the Rogers. Okay, so these are the first few terms. That means now what you can do is you can write the potential in the most general form as a function of the radial part and a function of the angular part, and it's a linear superposition of all such possible values of L. Right? That gives you the most general expression of the potential in the spherical coordinates. Now, based on your question, you try to impose the boundary conditions. So now, if you are asked or if you are said that you know the potential, you have a hollow sphere, the potential on the surface is given as V1. Okay, and you are asked to find the potential inside the sphere. Okay? So here, because we are trying to find the potential inside, if I go back to the most general form, here it means that because we're trying to solve it for inside, your expression of potential should be consistent and should be valid for R equal to 0. And you see that this term would blow up if you put R equal to 0. That means whenever you're trying to find the potential inside a spherical region, okay, there you have to have B equal to 0. Okay, so in that case, your general form of potential will look like this. Okay. Now, putting R equal to capital R, we know that the potential is equal to V0. So this is our boundary condition. Right? Now we'll again use the orthogonality relation for Legendre polynomials, and this is the orthogonality relation. If you do that, that will give you the expression for like the values of the coefficients AL. So now if you put the expression of AL in this general form, that will give you the potential, right? So let us look at an example. So here it is said that this is how the potential is. Suppose your expression of V0 is given. Okay? You have to find what is the potential inside. So what you have to do, basically you have to find the exponents, right? Coefficients, right? You have to find AL. Now one way of doing it, and the most general and rigorous in most cases, will be use this expression of not try to put it here. Okay, do this integrations for all values of L, P equal to 1, 2, all individual values, and try to solve for AL. Right? That is the most general way. But there is an easier way of doing it. So what is that? Basically, this is your potential, right? So we'll try to write it in a simpler form, keeping in mind our expressions for the Legendre polynomials, right? See, this is how the Legendre polynomials look like. So PL cos theta, P0 cos theta will be 1, P1 cos theta will be equal to cos theta, right? So that means here, when you have this potential expression, you can write it in a simpler form as k by 2 1 minus cos theta, right? Where the first term is nothing but P0 cos theta, and the second term is nothing but P1 cos theta. So that means you have already written your potential in terms of Legendre polynomials, right? So now if you compare with your expression, you see that if you just compare with this expression, you see that only A0 and A1 is non-zero because you only have terms with the first and the second terms of the Legendre polynomials, right? All other A else go to 0. So you do not need to solve for A2, A3, A4. All of them will be 0. And A0 will be equal to K by 2 and A1 will be equal to minus K by 2R. How do you do that? Basically, you expand this, okay, and then compare with this form, right? That will give you the value of A0 and A1. And once you find A0 and A1, you can put it in the general expression, which you have here, right? And that will give you the expression for the potential. So in this kind of questions, always try to see how the expression of the potential is and see if you can write it as a combination of Legendre polynomials. Right? If you can do that, just by comparing with the forms, you can try to find the coefficients. If it is not so simple, then you have to follow the, you have to do the complete integration. Okay. Is it clear till here? Okay, so I'll consider it clear. So now this is for the case where you want to find the potential inside this field. If you are asked to find the potential outside, in that case, you have to again go back to our most general form. Okay, so if you go back to our most general form, that is here. Now the expression should be such that when we put R10 going to infinity, your potential should not blow up, right? So that is telling you that this term should not be there. So when we talk about potentials outside, okay, where your R can go to infinity, in those cases you have this term will not be there. So there AL will go to 0, right? And in situations where you are asked to find the potential inside a region where your R value can go to 0, there all BL terms will go to 0. Okay? So when you are asked to find the potential outside, in that case, this will be the potential. Okay? And then you can use similar. Okay, so you can write and try to ratio, and that will give you the expressions of your potentials. Once you find the expression of the coefficients, you can put it in the general form to find the potential. Okay. Okay. So in general, like if I have to sum up what we discussed till now, in this kind of questions where you are asked to find the potential in the region where the boundary conditions of the surface are given, we have to use the Laplace equation. Obviously, it's important to know that in the region of interest, there should not be any charge, right? Because only then the Laplace equation will be valid. You know the potential on the surface surrounding the region. So you use the boundary condition, solve for B. Once you find B, you can try to find the electric field. Once you find the electric field, you can use this solution to find the surface charge density on the surface which covers or encloses the region. Okay. Now,
Excuse
this
me,
was
ma'am.
some question from the last year assignments, which I saw. So we'll try to see how to address this kind of questions. Okay. So here it is said that you have two conducting plates placed at z equal to -2 and z equal to +2. Okay. And they are maintained at different potentials, 0 and 100. Okay. Now, assuming that the plates are separated by some dielectric something, the question is that can we find an expression for B using Laplace equation, and can we use B to find charge densities, right? So the first part is, see, you have your conditions in Z, right? So that means what you have to use here is a one-dimensional Laplace equation, right? Now, what is the one-dimensional Laplace equation? Del square B del Z square is equal to 0, right? And what are the two conditions? The conditions are that at z equal to -2, your potential should be 0, and at z equal to +2, your potential should be 100. So can you try to find the expression for the potential? The condition is del square B del Z square is equal to 0 with these two conditions. Okay, so can you guys try to solve and tell me what the expression of the potential should be? It's simple, right? Try to solve it. Del square B del Z square is equal to 0. So that means del B del Z will be constant and B will be something like AZ plus B kind of form, right? So if you have that form and if you have this two conditions, can you tell me the form of the potential? Let me know if you are stuck somewhere. If you have any doubts or if you have any problem, just let me know because it's pretty simple, right? If you're able to do it, if you're stuck, please let me know.
Ma'am, is it possible to discuss the solutions of the previous assignment?
Yeah, this
with
was
the
one question from the previous assignment. And I think what we were told last time was that, you can discuss or, similar questions and try to give an idea, but not exactly solve the question. So that's why I'm choosing this question from the last year's assignments and trying to tell you how to do it. Okay, so if you just, respond and reply back, I'll be able to tell you where you are stuck and, help you out with it.
Ma'am, actually in this assignment, they have given the distribution, charge distribution in the P and the N regions of a PN junction. And there were series of questions based on that distribution, charge distribution, to find out the
Okay,
electric
I think
field.
I think if you follow the last year's video, we did
Acha.
discuss some question on PN junctions.
Okay.
Like you're
Okay,
talking
so
about, so basically there are some donors and acceptor regions. So you have some positive charge distribution and some negative charge distributions.
yes.
Right?
Yeah.
And you have to see how
Yeah.
the electric field goes, all
Electric
those
field
kind of questions,
potential.
right?
Yeah, potential and capacitance. All, I mean, there are a series of connected questions to that.
Yeah, right. So I think if you follow last week's video, I think it was already uploaded. So,
Okay, last week's
yes,
video. Okay,
yes,
thank you so much.
yeah,
Okay.
okay. Now coming back to this question, can you guys please contribute and tell me where you are stuck or what is the problem? Because see, this is very simple, right? So you have del square B del Z square equal to 0, right? Your form of the potential should be something like AZ plus B, right? And you have to find A and B, right, in order to find the potential. And you have two conditions given. Z equal to -2, B is 0, Z equal to +2, B is 100. So that will give you the value of A and B. So that means now you know the expression for the potential. So once you get the expression for the potential, you have to find the charge density, right? So what is the relation that you should use in order to find the charge density? We have to use the relation of sigma is equal to minus epsilon del V del Z, right? At those values of Z. So suppose what I mean is that you have two regions, right? This is suppose 2 points in Z. Now you want to find what is the charge density at this point. So there you have to use the relation sigma is equal to minus of epsilon, right? Del V, you know the expression of del V del Z, right? Del V del Z is nothing but For this case, it will be nothing but A, because your V has a form of AZ plus B, right? So del V del Z at Z equal to Z equal to plus 2, right? Similarly, here again at this point, it will be minus epsilon del V del Z at Z equal to minus 2, right? And you have to be careful about the direction of your field. Del V del Z is nothing but field, right? E is equal to minus grad V. So minus of del V del Z is nothing but electric field. So you have to be careful about the direction of the electric field, because as someone pointed out, right, we had the expression of del V del N. N is the normal vector. So when you are trying to find the charge density here, right? So there the normal vector is directed in this direction, because the field outside is zero. You are considering. So when you write E out minus E in, your outside will not be there. So basically, your normal component of the surface is pointed downwards. Okay? And when you talk about this surface, I said equal to minus 2, your normal component is pointing upwards. Right? So in one case, your N cap will be minus Z. This will be minus Z, while here it will be plus Z. Right? Is it clear, guys?
Yes, ma'am.
Okay. So now there can be this kind of similar questions, where the potential, this was another question from the last year, where, here the normal expression or the general expression of potential is given. Okay, and it said that what are the equations of potential, equipotential surface at V equal to 0 and some other non-zero quantity. So how do you find the equations of equipotential surface? You just have to, in the first case, you have to put 20x square yz minus 10z square is equal to 0, right? And then you can take 10z as common, right? Z cannot be equal to 0. So that means the general form will be 2x square y minus z going to 0 for the first case. For the second case, again, you have to equate the expression of v to 30, right? And do a similar simplification. So these two gives us the equations of equipotential surfaces at two values of potential. So that means if you are, suppose, in a follow-up question which I saw, there were questions where it is said that at some given value of x and some given value of z, okay, what would be, suppose you are asked what should be the electric field, right? So how do you do it? So suppose you are said that, so this is your expression of the equipotential surface at t equal to 30. That means if x and z or x and y, any two of them are given, you can find the third quantity from here, right? Use this relation to find x, y, and z. So you know that. Now the point is, this is your general expression of v. So once you have the general expression of v, what you can do is you can do minus grad v, right? That will give you the general expression of electric field. And you have found the value of x, y, and z. So put those values of x, y, and z in order to find the electric field at that surface. Or you understand, right? Now, so if this is your expression of V, what would be the electric field? Minus del V del x I cap minus del V del y j cap minus del V del z k cap. So that is your electric field. That will, each of these terms will be a function of x, y, and z. Try to put the values of x, y, and z, which you got from this expression, right? Any two of the terms will be given. You have to find the other. Okay, so once you do that, put the values of x, y, and z, and that will give you the expression of electric field, right? And then if you are asked to find the normal to that surface, you know that what you have to do? The direction minus grad v. So that's a vector, right? So that itself is the direction of the normal. If you are asked to find unit normal, you have to divide by the magnitude, right? So similar kinds of questions can come. So I think this was some kinds of questions. So use the same relations that we just discussed. This would be the process of solving this kind of questions. If you have any doubt, please ask. Any question, guys?
Ma'am, can you tell me how we find the voltage equation in case of question above question?
How to find the voltage?
Equation for voltage using Laplace in the above question, the first one.
I'm very problems. The last students are not able to hear. So in the first
How
question,
we write
you have to
the
find
how we write the potential how we write the potential equation for above question number 1.
Okay. So in the first question, so if we look at the first question, what is our condition that is given? Right? The first question is that you have two conducting plates. You know the potential at the two plates. You have to find the potential somewhere inside. Right? So that means you have to use the Laplace equation. Now it's in one dimension, right? The boundary conditions are in one dimension. So what you have to use is the Laplace equation in one dimension. So what would be the expression of Laplace equation in one dimension? Del square b equal to 0, right? So in one dimension, what it will be?
2v by dx is equal to 0, dv by dx is equal to 0.
So del square b, del z square is equal to 0. That is our Laplace equation, right? Now, that means now we want to find v. So we will integrate, right? So del square b, del z square equal to 0. That means del v, del z is equal to some constant. Take it as a, right? And integrate it further. So that means v turns out to be a z plus b. Is it clear? Del square b, del z square equal to 0. That means del b, del z is equal to some constant a. That means v is equal to az plus b. Is it clear? Now, once you have this form, az plus
We
b,
have to differentiate with respect to z only. Yes, I
yes,
have to
exactly,
differentiate.
because your Laplace equation will be based on what are your boundary conditions, right? Your boundary conditions are in z direction, right? Your potential has a dependence in z. So what you write is del square b, del z square is equal to 0. Pardon my handwriting. So del square b, del z square is equal to 0. This gives you a form of az plus b. Then put the value of z equal to -2 and equate the potential to 0. Again, put the value of z equal to 2 and equate the potential to 100. So you can find a and b, right? So that will give you the potential as some form as az plus b.
Yes, ma'am. Okay, it's okay.
Understood, right?
Yeah, ma'am.
Yes. So now, using these two boundary conditions, you know what is a, you know what is b. So you know the potential. So that gives you the answer for the first question. The second part is how to use B to find charge densities. Right? So in order to find charge densities, what do we have to do? We have to find sigma is equal to epsilon minus epsilon del B del Z. Right? And there is a direction of normal which is to be taken into account. Right? So when we are trying to find the charge density for the top surface, Z equal to 2. Your normal vector is along minus Z. When you are trying to find the potential for the down surface, x is equal to -2, your normal component is along the z direction. Right? So at this point, you use the relation sigma is equal to minus epsilon del v del z. At z equal to -2, z equal to 2. Here it will be again sigma minus sigma del v del z at z equal to -2. So at this point, what will happen is, basically, you have this normal components. If I write the expression, it will be something like sigma is equal to minus of del V del Z into, there's an epsilon dot here. Sorry, I just missed it. So there's an epsilon dot, and there will be an n. The normal has to be considered because this has a direction. This is the electric field. So that will have a minus Z direction, which will result in a plus sign here. So basically what you have to do is del V del Z into epsilon, right? Which is nothing but 2.25 into epsilon naught into your A, right? If you do del V del Z, you get A. So that is your charge density on the top plate. Similarly, you can do the charge density on the bottom plate. So there you will have the same value, but you have a minus sign here because then the normal component is along plus Z direction. Is it clear?
Yeah, ma'am, it is clear now.
Okay. So now we'll move on to a different topic, which again comes from the properties of the harmonic functions which satisfy the Laplace equation. And it says that if you have some volume, okay, and you know the potential on the surface enclosing the volume, okay, then the potential inside in the volume is uniquely determined. Okay? The solution to Laplace equation in some volume V is uniquely determined if V is specified on the boundary surface S. Okay, and the proof for the same comes from the previous conditions of Laplace equations. Okay, so consider that you have two solutions. Okay, so if this was not the case, you would have had to consider two solutions. So that means for this region, you will also have del square. So V1 and V2 are the two solutions. So that del square V1 is also equal to 0. Del square V2 is also equal to 0. That means now you can do a linear combination of the two. So that is V3. So you consider V3 is equal to V1 minus V2. That means V3 should also satisfy the Laplace equation in this volume, right? So del square V3 should also be equal to 0, and it is consistent. But what it is telling us is that we know the potential, if the potential on the surface is specified. So the V1 at the surface is equal to V, which is specified, and V2 at the surface is also V, right? So V1 has a value of V on the surface, V2 also has a value of V on the surface. That means what will be the value of V3 on the surface? It will go to 0, right? Now if we remember that Laplace equation allows no maxima and minima, that means if the value of V3 is 0 on the surface, anywhere inside the volume, it should also be 0, right? There cannot be any maxima and minima. That means V3 is always 0, 0 everywhere, which tells us that V1 must be equal to V2. So that is that if you know the potential on a surface enclosing a volume, the potential inside in the volume is uniquely determined. That is the uniqueness theorem. And we see how this lies at the heart of the method of images that one uses. Okay. Now talking about the second uniqueness theorem, there is also another uniqueness theorem which says that if in a volume you have different conductors and you know the charge, volume charge density in the region, and you know what is charge on the individual conductors, then the electric field is uniquely determined in this field. So basically, using this uniqueness theorem allows us to simplify calculations of potentials and electric fields. We'll see it in the coming slides how it becomes useful. Okay. Now, talking about the method of images. So here, if we start with this case where you have some surface, some potential surface, consider some conducting surface where the potential is said to be 0. Okay. And then you have some dust-king charge at some distance d from this surface. And you are asked what is the potential in the region of the plane. Right? So if there was no such plane, we know we can just use the normal relation of 1 our basic understanding of potential, we can try to find the potential. But now you have this conducting plane, right? Now, because of the presence of this Q charge, there will be some induced charges on this conducting plane, and the induced charge is such that the potential here is zero. That is what the question is saying, right? So that means the presence of this plane changes the potential that you have here. Right? Now, if you remember what we just discussed in the uniqueness theorem, it says that we want to find the potential in somewhere in this region, right, above the plane. It says that if you know the boundary conditions which enclose this region, okay, then the potential inside is uniquely determined. It has only one value. So this allows us to, mimic this situation with a simpler charge distribution. So this is the question you want to solve. We say, what if now we put a minus Q charge at an equal distance from the xy plane, such that at the xy plane the potential goes to zero. So that means the boundary conditions for this problem and this problem are the same. So that means if we try to solve this problem and try to find the potential in a region of this plane, the potential for this case will be the same, right? So that allows us to use this method of images. So this minus Q charge that we have put is an image charge. Okay? And now because it's just, this is much simpler to solve. We don't have to consider how the induced charge have distributed themselves here and that. So that means we can just use these two discrete charges to find the potential at any point above the plane. And this is how it will look like. Similarly, you can use this expression to find the charge density. So if you use the solution to find the charge density at the xy plane, you will see that if you integrate over the entire area, you will find the total charge induced is actually equal and opposite to this plus Q charge. Okay. And you can also try to find how the force is. So basically, these are direct ways of solving it, right? So the main point is you can simplify your problem of charge distributions to a much simplified fashion, simplified distribution by using the uniqueness theorem, where you include some image charges. Okay. It's important to note that the work done for the two cases will be different. The potential is the same, the force is the same, but the work done in the two cases will be different, because here you have to do work to bring both of these charges at these 2 points, while here you are just bringing the only one charges, right? So that's why the work done will be different from what you do here, but other terms will all be the same. So that is your method of images. Now, similar thing can be done for a sphere. So here it says that the potential on the surface of the sphere is given 0. You have a plus Q charge at some distance center. You say how to find the potential somewhere outside the sphere. So what you do, you say that we will mimic the situation with some point charge, okay, somewhere inside the sphere. And if you try to solve it, you'll see that this Q prime charge at a distance b from the center. So somewhere inside, you have a Q prime charge with some distance from the center, and if you put that charge, so these values come in such a way. So how do we get to these values? So we choose a Q prime and a b such that the potential is still 0 on the surface. Okay. So if you do that, then you have a much simpler solution, and you can use it to find potential. Okay. Now what happens if we now say that the potential on the sphere is not 0, but some non-zero value V naught. So you have a charge Q, you have a metal sphere, and the potential on the sphere is given by some V naught. It's not V equal to 0. So can you tell me how the image charges should be chosen in this case? Any idea, guys? So you have this plus Q charge. It says that it has a net voltage or net potential on the on the sphere, right? You want to mimic the situation with some point charges, right? How do you do it? So first we will say that we can again put a q prime charge such that the potential is 0. So we first do what we have done here, right? We put a q prime charge at a distance d from the center. So that makes the potential 0 on the sphere. And now what do? We put another charge now at the center of the sphere such that the potential here is V0. And we know how to do it, right? If your potential is given, you know that your potential on the surface is V0. You know how much charge to put at the center, right? Because if you put any charge at the center, this charge will create a potential of 1 by 4 pi epsilon 0 q by capital R, right? So now in this case, your V0 is given, so you can choose your Q such that your potential on the surface goes to V0. So basically what I mean is first you put a Q prime charge, then you put a Q double prime charge at the center such that, this condition is satisfied. Your V0 is given, you know what is R, you try to find Q double prime. So now in this case, you have to put two image charges. Okay. So based on your boundary conditions, you have to choose your image charges. Now the next part says that find the force of attraction between a point charge Q and a neutral conducting sphere. So because it is said that the conducting sphere is neutral, that means the summation of this charges should go to 0, right? So you have to impose that term. So Q prime plus Q double prime goes to 0. Now with this condition, now you know how to find the forces, right? Direct Coulomb's law, we use the law to find the. Okay. So this shows how simplified things become when you use charges, right? Now this is another question where you have two infinite rounded conducting planes. Okay. Initially we have solved with one plane. Now you have two planes, okay, intersecting at 90 degrees. There is an angle of 90 degrees. Then it is said that, okay, so how do you find, if you are asked to find the potential somewhere in this region, how do you do that, right? So how should be the image charges system? So you know that the potential here is 0 along the x, the potential along the y is 0. So you have to put charges in such a way that with those charges, the potential remains 0 along x and along y. So can you tell me what all charges should be put? How the image charges should be? Make use of your symmetry, right? So basically, you need something which, so here you have some Q charge, okay? And for this Q charge, you are expected to have a potential here, but you want to set the potential to 0. So what you will do, you will put a minus Q at an equal distance from the x plane, right? Now, because you have put a minus Q here, you also need to, you also need the potential to be 0 here along the y direction. So you need to put a plus Q in this direction. So basically something like this, right? From plus Q, you put a minus Q, which makes the potential 0 along positive x. Now, because you also need the potential to be 0 along y, you put a plus Q here, okay? And then because you also need the potential to be 0 along minus x, right? So that means again here you put a minus Q, right? So that this is how you choose your image charges. Now, once you have that, other things are simple. So now you can use your, the normal expressions of potentials between point charges to find potential, to find force, and all of that. Okay. Now, suppose you have said that, in spite of being at 90 degrees, if your planes are at 45 degrees, so how will you distribute the charges? So if you have, suppose this is your charge, okay, so this is the charge that you have, that is the point charge in your question, and you have to be equal to 0 planes at 45 degrees from each other. So how should the image charges be distributed? So in this question, try to use the symmetry. So first is you want to make the potential go to 0 along x, so you put a minus Q here, right? Similarly, here you want to have this potential along the 45-degree line to be 0. So you again put another point charge here, minus, equal and opposite to given charge. Okay, but you also want the potentials to be 0 along y, right? So what you do, you put another point charge, which is opposite to what has been what you have considered here. And similarly, now because it is you have this plus q here, you want the potential to be still 0 along x, so you have to put a minus q on the opposite side, right? And similarly, again to maintain the potential at 45 degree to be 0, you put a plus q here and again a minus q to balance the potential along x. So basically making use of the symmetry, right? So in general, the number of images required is some, you have two such plates at some angle theta. The number of image charges required is at this 360 degree by theta minus 1. So in this case, it was 90 degrees. So you have 4 minus 1, 3 point charges. Similarly, here it is 45. So it is 350 degree by 45 minus 1. So it's like 7, right? So this is how the image charges are being used. Now, important thing to know is that this method will not work for any angle. It will work for some specific angles. Why? Because suppose you had, these two conducting plates, but at an angle of 135 degree from each other. So there, you repeat the same thing, right? So you have this plus q. You want to have a 0 potential along x, so you put a minus q. Now, because you also want the potential to be 0 along this line, you put another minus q charge here. But now to balance this, you have to put the next image charge at this point. The problem is that this is within your region of interest, where you want to find your potential. The image charges cannot be placed in the region where you want to find the potential, because in that case, you are actually changing the entire charge distribution by itself. We cannot add new charges to our region of interest. We want to add image charges outside the region of interest in order to maintain the same boundary condition. In this kind of, so if this is the situation, there you have to put the image charge somewhere inside. And because this now messes up your, charge distribution, so this will not work. Okay, so that means this method, if you want to use this method for two such conducting plates, will only work in cases where theta must be an integral divisor of 180. It will work for all these angles, but it won't work for 135. Okay, because of this region. So always remember that the image charges should not be placed within the region where you want to find the potential. It should be placed outside. Okay. Okay. Now this is also a similar question where so we did a similar kind of question. So in this case, this said that what is the net force, right? So here you can have this kind of charge distributions and now try to find individual forces, like what is the force on Q for all the three forces, right? So this is pretty simple. You have F1 and F2, okay, given by this value. So your K is 1 by 4 pi epsilon naught. And then you have F3, which is directed in this direction. F1 and F2 will have a resultant in a direction opposite to F3. Okay, so the net resultant will be this, right? And will be directed towards the top. So this is how it becomes simplified. Otherwise, you would have to imagine how the charge distribution is on the surface, how the charge distribution is on this surface, okay, how the induced charges are, and that is a very complicated system. But image charges make sense, please. Now, there's also another question here. It's said that you have this kind of charge distribution, so always make use of symmetry. So if you have a distribution like this, if you are said that the potential here is 0, what you do is you put equal and opposite charges at equal distances on the other side of the plane, right? That makes keeps the potential to 0, and then you can use your coulombs or normal electrostatics. So here it is said that you are asked to find the potential. So here one important point is, so in this kind of charge distributions, always try to see what is the net charge. And if the net charges are distributed in such symmetric fashion, so you see that this is like the monopole move. So what you do, you try to find the net charge. If the net charge of your distribution is zero, that means the monopole term should always go to zero. So here, as you can see, because it has equal and opposite numbers of charges, so the monopole term is zero. Now, if you're asked to find, in this kind of potential, in this kind of charge distributions, you have different contributions from different, moments. So that's why if the monopole goes to zero, consider the dipole. So how do you find the dipole term? So for each such charge, you'll have a dipole moment which will be given as the charge into the distance. Right? So 3q into d. Again, you have minus q into 2d. Similarly, you have minus 3q into d and q into 2d. So that gives you the net dipole moment. Once you find the net dipole moment, this is your net dipole moment. Okay? Now, for any such dipole, you know that the expression for the potential for a dipole is given by 1 by 4 pi epsilon 0 p dot r cap by r square. So that gives you the approximate expression of potential for such charge distributions. Okay? So that's how you can try to solve this kind of questions of potentials of discrete charge distributions, or for continuous you have to do integrations. So now coming, slightly changing here and talking about Biot-Savart's law. So till now we have been talking about stationary charges, and we saw how stationary charges can lead to constant electric fields, and that was the regime of electrostatics. Similarly, steady currents can result in constant magnetic fields, which we call magnetostatics. Okay, so that means if you have some current carrying wire where steady current is flowing, that will result in some magnetic field. And how will the field look like? This is the expression for this is the law which tells us, how the magnetic field for a current carrying wire looks like. So here I is your current, DL is a line element in the current carrying wire, R is the distance from the field point. Okay, and this is the relation. So now if you use this for infinite wire, you take a line element along the infinite current carrying wire, your R is the distance from this line element. Okay, and if you try to use this Biot-Savart's law, you'll see that it will take up a very simplified form, where theta, this theta here is the angle that this line element sustains at the field point. That means based on the length of your wire, different angles will be subtended. Okay, so if you have an infinite wire, the angle subtended here will be pi by 2 and minus pi by 2 for the two ends of the wire. Consider it to be at infinity, right? So there you have a very simplified form of magnetic field. So this is the magnetic field for a infinite current carrying wire at a distance s from the wire. Okay, if you have a finite wire, there you have to consider what is the angle that the end of your wire makes at the field point. Okay, and similarly you can find the expression for the magnetic field. Now, in the assignments that I had checked, there was very simple questions which made use of this formula. Basically, you have a current carrying wire along Z at some distance, 5 centimeter, 5 meter from this wire. What would be your magnetic field? So you can directly use this relation, right? And be careful about the direction of the magnetic field. Okay, so what I mean is, you have to use the you can say the right hand thumb rule. You can use. So basically, if you have a current carrying wire in the z direction, in the xy plane, the fields will rotate according to your these 4 fingers of your enclosed in the thumb. So it's like this, right? If your field is in the minus z direction, then it becomes a clockwise current. Right here, it becomes a counterclockwise current. So based on the direction of your field point from the current carrying wire, try to find the direction of the field. Okay, so there are questions in the last assignment based on this, but these are pretty simple. Just put the values in advance. Okay, so now let us solve for for some current carrying systems. So here you have this wire loop where current is flowing in this direction. You are asked to find P, right? So what do? Here, if you want to find what the P is at the center, so you say that you choose one such wire and try to see what is the angle that the ends of this wire, this side, makes at the center, right? And it will be 45 because it's a square, right? So 45 this side and minus 45 this side, right? So if you do that, and if you put it in this expression that we discussed, right, you'll find an expression for B, and that will be for one side of the square, and then you'll have a similar expressions for all the four sides. So you can just add them up to find the net field. Why can you add? Because see, your current is flowing along this direction, so that means the magnetic field should be along up. It should come out of the plane of your square. If the current was in the opposite direction, your magnetic field would be directed inwards. Okay? So because for all of this, the magnetic fields will add up, so you can just do it for one side and 4 into that value will give you the net magnetic field. Similarly, you can try to solve for similar kinds of systems. So here you can break this into three sections. One is for this wire, another is for this wire, and another is for this semicircle, right? And you are asked to find the field here. So what do? So for the semicircle, you can first try to use Biot-Savart's law or a more general case where you have a current carrying circular loop. You are asked to find the field at some distance z from this loop. Okay, and this is just how you choose your DL line element, and R will be nothing but R square plus Z square. Okay, so if you use that, you'll see that this is the expression for the magnetic field at a distance z from a current carrying wire. Now, in your question that we were trying to solve, there z is equal to 0. So you are trying to find the field here at the center. So if you put z equal to 0, you will find that the field for a complete circle is given as u naught I by 2r. Right? Now, because you have a half circle, it will be u naught I by 4r. Right? And then you can try to find the contributions for these individual wires and add it up. Okay. So this will be your half circle contribution, and now you have two half infinite wires. So if you add the contributions of the two, you will get it for a one infinite wire, which is nothing but mu I by 2 pi r. So this is the net magnetic field at this point. So basically, one has to be careful about where the field point lies in order to be careful about the direction and use these relations. Okay, you can start with Biot-Savart's law and try to derive it once, but it's easier to remember this because this comes very handy. So this is for a circular loop at a distance z from the loop, and this is finite current carrying wire. This is for a finite current. So that's it. Any question, any of you? Okay. If not, thank you for today. Okay, guys.
Thank you, ma'am.
Thank you. Thank you.
Thank you, ma'am.